Okay, welcome everyone to this continuation of quantum topology. Quantum topology. Today, one of my favorite topics, essentially what makes quantum topology. So there's neither quantum nor topology, like in the usual way how people name things, there's neither quantum nor topology. But really this idea of having efficient presentations of objects. And I tell you what I mean by that. And also tells you this idea of what a category actually is a little bit better. Because I think of a category as a two-dimensional object. And today I would like to drive that point home for the whatever how many time. But it's always worse to just repeat it. And the connecting point are generator and relations. Generators, relations, whatever you want to call them. And what I have in mind is the following. So if you think of a group, you can encode a group in like in the multiplication table. Here is z mod 4, and it's additive, right? Multiplication table, whatever. And yeah, so here's the multiplication table of z mod 4. Well, 0 plus 0 is 0. 0 plus 2 is 2. 1 plus 1 is 2. Something like that, right? So a bit boring. And you need quite a bit of information to encode a group of order 4. You would need 4 squared information. You just have encoded the order of 4, group of order 4. You could also be much more efficient in some sense. You could just say 1 is a generator, because everything can be constructed using 1. Because 0 is 0 times 1. 1 is 1 times 1. 2 is 2 times 1, really 1 plus 1. And I just write this nicely, just stack them next to one another. 1, 1. It's not 11, it's 1 and 1 next to one another. You'll see that coming back later. And then 1, 1, 1, right? So 1 plus 1 plus 1 is 3. Yeah? So, and I've encoded the whole group, essentially, just in this rule. If I add one extra thing, a relation, namely that 4 times 1 is 0 again, right? I'm going back to where I started. So I only have one generator, one relation, and I encode the whole group using one generator and one relation instead of 16 symbols in my multiplication table. Yeah, so generators and relations. I really just write everything in terms of one generating object. Yeah. So multiplication table above. I probably should zoom out a little bit. A group given by generators and relations, and the whole game that is kind of really important in quantum topology is find generators and relations presentations for nice categories. So if you, hopefully this works, if you Google generators relations, you probably will find it for presentations of a group. So maybe that's what you have seen. It's called presentation of a group. And in standard groups, should be standard. There should be a list or something. Blah, 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 blah. Who cares about the definition? Examples like standard thing, right? So if it's free, there are no relations, so you just stack up things. I'm not sure why this is the next example, but yeah, you can have the pi1 of a surface, but maybe the cyclic group, that's what we just had, a dihedral group, whatever, other things, a lot of things. This guy here, for example. So generator of relation presentations, they're like everywhere, and for some reasons, people usually don't tell you about them when you first learn about groups or whatever. I first learned about it in topology. It's kind of a wrong place to think about it, or kind of, if you want, you should have learned this in group theory. But in topology, maybe this is why this is the first example. You often just have groups given by generators and relations, because the relations come from a kind of topological properties of your spaces. Anyway, so this is one of there are a lot of things in mathematics that life probably, that you learn later on. And you really wonder why nobody has ever told you. This is one of them. So generators and relations is something, at least I felt after a while, why hasn't nobody ever told me about it? This is just a very nice way to kind of see what a group is. Yeah. And there's actually a really nice way to visualize what it is. So it works as follows, in general. For a set, for a group, for a monoid, something in classical mathematics, which is a one-dimensional thing. So usually just take an alphabet, and I call alphabets usually S, for no good reason. I just call them S. And these are the symbols we pick. So here in my little illustration, there would be a black symbol and a white symbol, a black pearl and a white pearl. And usually you don't include identities, they kind of come for free. You kind of assume that they're there, right? So identities would be something empty on my string if you want, so you kind of don't include them. So in my example here, I really just have black and white. And a word is literally just that thing. It's a concatenation of pearls on a line. Whatever, let's start reading here. Something like white, black, black, white, black, black, white, black, black, white, and so on. And the relation would be ways to manipulate those things. So for example, if you would imagine that 2 black is white, you could replace these 2 black by white, and so on. Yeah? So that's the generated relation games for groups, sets, monoids, whatever you want. Some classical mathematics, right? Where you write things in a line. Yeah. Classical mathematics, you write things in a line. Yeah, excellent. So we write things on a line, on a pearl, whatever, on a pearl bracelet, and yeah, and you have the relations are just the ways to manipulate the various pearls. Yeah, so really that's what we do. And that's how you do it for sets. And really, it doesn't really matter, for example, where they are, just the order matters, right? It's not important that there's space in between, because there's an identity sitting there and that's like empty and you can delete it. But this is how it works for sets. It's like pearls on a line. Literally, that's what it is, pearls on a line. So categories, I have a 2-dimensional picture in mind. Categories should be brick walls. Beautiful. So generated relation for monoidal categories are, I think of them as being brick walls. Why? Because in the monoidal category you can compose morphisms or you can multiply morphisms. Compose morphisms, multiply morphisms, you get a 2-dimensional picture. And I think about my generators and relations now as having object generators, exactly the same as before. Morphism generators, and I call them T for no good reason, but I call them T. And we think of them as being bricks. So there are 2 ways to stack them together. You can take a morphism generator and stack it next to one another, to another one, or you can take one and stack one on top. So you can then build a brick wall, right? Your monoidal category is now not, as in classical mathematics, a line, but in categorical mathematics, it's now a brick wall. Beautiful. And the relations, I still call them R, and they're the ways now to manipulate the bricks. Yeah. Not the object. The objects will stay fixed. There are no relations on the objects. The morphisms will enforce relations on the objects. So for objects, you just have your Perl game. And for morphisms, you have your brick game, and you have relations on bricks, right? So you can have whatever. If you have 5 bricks stacked in a certain pattern, then you can maybe make them 3 bricks stacked together in a different pattern. Something like that. I'll show you relations in a second. Yeah, so that's how I think about monoidal categories. Monoidal categories are literally just a brick wall given by generators and relations, and the generators are the kind of the bricks, right? There could be different bricks. There could be this type of brick, and there could be that type of brick. Maybe that's the same or different, but kind of different generators and relations. And I wanted to write down a formal definition, and then I realized that that's it's really a bit annoying. I will just explain it on the example. It's much easier, and then it generalizes easily. I wrote it down here in the quantum topology, and it was, you don't want to read that. So instead, I just I asked ChatGPT to make a list of the 10 most annoying things. When autocorrect changes a perfectly fine word. There you go. It's something like that. It's annoying, right? But it's not difficult to get rid of that annoyance. Writing it down a formal definition is kind of the same, so I decided to skip it. But let's look at this example, which I call the Brouwer category. So we have object generators, S, we have morphisms generators, T, and we have relations on morphisms, R. So object generators is just a bullet, and I think of these as the end-points. So, and now you can just line them up like on a like pearls, right? Bullet, 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 bullet. So the only thing you have is bullets, a few of them. So here you have 2 bullets. Here you have 3 bullets, whatever. So this is a morphism from 2 bullets, from bullet squared to itself. Bullet, 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 bullet. This is a morphism from bullet squared to empty, and this is a morphism from empty to bullet squared. And these are now the generators, and you can stack them together like bricks. So you can take a crossing and put a cup next to it. Or you can take a crossing and put an identity next to it, which is a string. So, or you can take a cup or a cap and put an identity next to it. You can stack them on top. So like a picture like this, where literally here's my little brick. It's just a cup, and I can stack an identity brick next to it, and then I do the same on the top and just stack them on the top. So these little pieces here, this is a little piece, this is a little piece, this is a little piece, and this is a little piece is my brick. And then I have those relations how to massage the bricks. So if I have a brick composition like this, then this is the identity and so on. So for objects, you stack them together on a Perl, and for morphisms, you stack them together like bricks. And kind of the crucial thing is I don't include identities in my definition of generators. In particular, there is a brick which is just a straight strand, right? I say that again, straight strand is a brick, and I could put it next to a cup. And I get a picture like at the bottom here, right? I could put a straight strand to a cup, and that's totally fine, and I just build it like Lego, like a brick wall, whatever you prefer as your analogy. And this is really cool, because this is actually the Brouwer category, BR, is actually a generators and relations presentation of cobordisms. But it's completely abstract, right? I'm just drawing the obvious diagrams, but I'm just treating them as symbols that I can stack together, as bricks that I can stack together, right? So Brouwer is monoidally equivalent to cobordisms, but now every object is actually an abstract symbol and not a real type of interval string cobordism topological object, just a symbol. And the map is kind of the obvious. That's why the symbols are defined the way they are. It sends a bullet to a bullet, it sends a crossing to a crossing, and so on. And what you need to do is, in order, for example, to show that this is a monoidal equivalence, that's not difficult, it's just a bit annoying, is you need to realize that you can write every, for example, for fullness, subjectivity, you need to realize that you can write every morphism in one cop, which is just a cobordism, in this type of height type setting, where at every stage now you have just one generator and potential identities. So there's a brick type decomposition of your cobordisms. And that shows fullness. You can easily show fullness. And if you think about a normal form, you can show facefulness, and that every structure is preserved is essentially, it's not difficult. And I think this is really cool. So we have a generators and relations description, an abstract description, a brick type wall description of a topological category, right? So this is pretty good. And we have lots of examples along kind of some of the same type of flavor of examples. Anyway, I hope you enjoyed this video, and I also hope to see you next time.